Okay, let's just jump right in. We need to unpack this central conflict that is really defining modern warfare
Right.
because it affects everything. I mean, everything from intelligence sharing across, continents to the actual speed at which a missile can be fired.
It's a massive, deeply ingrained tension.
It is. We are living in what is by far the most interconnected digital age ever. Our phones, our watches, they all talk instantly to global networks.
And yet on the other side of that coin, you have national security.
Exactly. Which demands absolute, total data protection. We're talking about data being separated by literal air gaps.
This fundamental contradiction, this is what the source material calls the data paradox.
It's the ultimate collision of strategic imperatives, isn't it?
It is, because on one hand, you have this absolute necessity for instant, seamless information exchange. It's critical to survival in a high-speed conflict.
To put it mildly.
But on the other hand, you have the statutory, the diplomatic requirements to protect national security data. We're talking about the sources and methods that give us our asymmetric advantage.
And if that data gets compromised.
It's gone. It's gone forever. You can't unring that bell.
So the deep dive question for us today is, I think, extremely precise. How do you instantaneously share classified information across allied networks?
And not just any networks. Networks that are often operating at totally different security levels, using different infrastructure.
Right, without compromising the fundamental secrets that protect the entire intelligence gathering mechanism in the first place.
That is the mission. That's what we're digging into. We are analyzing a proposal that's outlined in the source material, and it's a radical one.
It's a conceptual transformation almost.
It really is. It's about the technology that acts as the gatekeeper between these secure worlds. The technology is called the cross-domain solution, or CDS.
And the idea here isn't just to upgrade it.
No. We're looking at moving these solutions from being, static, binary security guard.
Like a bouncer at a club.
Exactly. A bouncer that just says yes or no. We want to turn them into dynamic, context-aware translation and generative engines.
We have to analyze this with a sense of urgency because the stakes are just unprecedentedly high. When we talk about the modern combat environment, what are we really talking about?
We're talking about hypersonic threats. We're talking about targets that can appear and vanish in moments.
Drone swarms.
Swarms of drones that require an immediate, coordinated counter-response. In that environment, the old axiom, to delay is to fail, becomes terrifyingly literal.
So we are rushing to transition from this manual human speed interoperability,
Which is where we are now.
toward a true machine speed classification architecture. Because if that targeting data arrives 5 minutes too late, what happens?
The adversary's strategic asset, whether that's a mobile missile launcher or a command post, it's already moved. The operational window is just gone.
It's slammed shut.
This is what drives that military imperative to achieve true machine speed.
And this whole transition, this whole idea, it underpins a concept that has become the strategic imperative for allied forces globally, and that's the kill web.
Right. And it's important to understand this isn't just about linking one sensor to one shooter in the old linear way.
This isn't a simple chain.
Not at all. We're talking about a dynamic, nonlinear network where any allied sensor
Any sensor, so a U.S. satellite.
operating at the highest classification level or, a partner nation's forward observer on the ground with a pair of binoculars.
So totally different ends of the tech spectrum.
Exactly. Any of them must be able to feed any allied shooter, instantly closing that loop.
And the source material frames this perfectly. It talks about facilitating a U.S.-derived find-fix capability.
Which, usually relies on our most sensitive intelligence collection methods.
And then having that seamlessly executed by a partner finish.
And that word seamlessness is everything. It's entirely reliant on the speed and the integrity of that classification data flow.
So it's the ultimate connectivity challenge.
It is. In an environment where connectivity, if you mismanage it, usually spells disaster because secrets get spilled.
Okay, so before we can even appreciate the slick generative AI solutions being proposed here, we have to thoroughly dissect the problem they are trying to fix.
You have to understand the pain point.
Exactly. And that problem starts with the current philosophy of classification itself. The sources use an analogy I thought was really good. They call it the copyright paradox.
It truly is a perfect analogy. Classification exists really as the intellectual property protection for national security data.
It's IP.
It's the crown jewels.
Sure.
The whole point of protocols like top secret or TS and secret is protecting our sources and methods.
So not just the data, but how we get the data.
Precisely. The intelligence collection mechanisms, the specific frequencies we monitor, the true capabilities of our sensors, these are the military's most valuable intellectual assets.
And once that data is
Once the source is known or the method is revealed, the protection is effectively gone forever. The entire system is built around guarding against that permanent loss.
But the operational environment is demanding that this very same data be shared faster and more broadly than ever before.
And that's the paradox.
Which brings us to the core technical hurdle. It's called the aggregation problem. I think this is a concept that, people outside secure environments can struggle with. Why does combining two pieces of unclassified data suddenly make them top secret?
That's a great question. And it is the root of this bureaucratic nightmare. Let's think of it outside a military context for a second.
Okay.
Imagine you have a list of all U.S. citizens who own a specific luxury car. That's unclassified data.
Right.
And you have a separate list of all citizens who recently purchased a private airfield. Also unclassified.
Individually benign facts.
Totally benign. But if you combine them, you aggregate them, and suddenly you generate a new list, a list of people who are both very wealthy and have dedicated air access, you've just created a new level of sensitive information that might reveal a financial trend or a vulnerability that didn't exist to the component parts.
Okay, that makes sense. Now apply that to warfighting.
Exactly.
Yeah.
The source points out that warfighting processes, just by their nature, bind disparate data sources together.
Oh, okay, like what?
So you might have a single piece of data from a human source that's, say, secure but unclassified, or SBU, maybe just confirms a location.
A dot on a map.
Right. But when that SBU dot is combined with dozens of other signals, intelligence reports, SIGINT and overhead reconnaissance photos, and sensor tracks to create a fighting common operational picture, or a COP.
A full picture of the battlefield.
The totality of that package suddenly increases its classification level. The combination of facts reveals a capability or a methodology.
Like our ability to track a specific vehicle type in real time?
Exactly. And that capability must be protected at the top secret level.
And this is where we run headlong into the real-world, deeply frustrating issue that is known as the swivel chair reality. Can you just detail the current slow-motion model for us? Because I think people imagine it's just, highly secure, vetted email systems.
And that's the fundamental error. It's not email. It's the physical, human-intensive segregation of networks. The current model is built around air-gapped networks.
Meaning no electronic connection.
None. They are designed to prevent any possible electronic connection between high-security domains and low-security domains. So you have your high-side systems, like JWICS.
Which stands for?
The Joint Worldwide Intelligence Communication System. It's reserved for top-secret sensitive compartmented information, or TSSCI.
The highest level.
Right. And then you have your lower-side systems, like SIPRNet, which is the Secret Internet Protocol Router Network handling secret data. And then you have various partner networks like the NATO secret WANs.
So why does that physical air gap mean we need a swivel chair?
Because to move data from the high-side domains, say from JWICS to the lower-side domain secret or a foreign partner network, it is, in many cases, a manual human-intensive process.
A person has to do it.
A person. A human is required to sit between two physically separated computer screens. They read the highly sensitive information on the high-side screen. They evaluate its sensitivity against a paper security classification guide, or SCG.
So they're checking a rule book.
A physical rule book. And then, if it's approved for release, they must manually retype or rephrase that essential information onto the lower side air-gapped screen. They literally have to swivel their chair to do it.
This sounds less like the pinnacle of modern defense technology and more like, an extremely high-stakes, extremely tedious data entry job.
That's a pretty good description.
And it's being done by highly paid, highly trained intelligence officers.
It is, and the human cost is manifold. The source material highlights that this manual process introduces a high chance of human error.
Like what?
Fatigue during long shifts, missed details, typos in critical grid coordinates, and crucially subjective interpretation of sometimes vague rules.
Let's circle back to the cost of latency, because this is where the human cost of that administrative delay is just brutally felt. This is why the military is so desperate to move away from this. We're talking about a world where microseconds matter, but the swivel chair is introducing minutes.
Yes. And the source gives that sobering, concrete example that really defines the entire problem. We aren't discussing peacetime logistics here. We're discussing warfighting.
Right.
A 5-minute delay, just 5 minutes, caused by the need to swivel chair targeting data, say, grid coordinates for an enemy asset, to a gun crew operating on a lower classification network. That 5 minutes can mean a missed opportunity to destroy a high-value threat.
Like an enemy tank or a missile battery.
Exactly. And what happens in that 5 minutes?
The asset survives.
That enemy asset survives, and the operational assessment notes that it survives to inflict casualties.
So that administrative cost.
The time it takes a human to read the data, mentally sanitize it, and retype it.
It's directly paid in lives on the battlefield.
It is an unacceptable trade-off in the age of machine speed conflict.
5 minutes. That's the entire operational window, just gone.
I'm just imagining a foreign disclosure officer pulling an all-nighter just to approve one critical targeting package, knowing that a single typo could expose a national secret, or, on the other hand, that a 5-minute delay could cost lives.
The operational utility is held hostage by administrative caution.
So what's the objective then?
It has to be purely functional. We must find a way to rigorously detangle the medium, the specific classified network or the highly sensitive sensor that collected the data from the message.
The actionable data.
The actionable data utility. The target's location, its movement vector, its time of exposure. We need a system that can strip away the classification inherent to the sensor, but preserve the mission-critical utility of the data. And do it at machine speed, consistently, every time. Okay, so if the swivel chair is the disease, and that 5-minute delay costs lives, we need a cure that operates at, the speed of light. The source material says the military has tried to solve this before with automated systems, and they failed.
They did.
What was that first attempt, and why did it fall so short?
The first attempt was the early generation of CDS systems, and they failed because they used what the source calls the blunt hammer approach.
A blunt hammer?
Right. These systems relied on simple binary logic driven by static lists, often called dirty word lists or blacklists.
Okay, so how did that actually work? How did the blunt hammer operate?
Very simply, if the system found a particular top-secret phrase, a specific program name, or a reference to a highly sensitive collection method in a document that was trying to move from the high side to a lower side system,
It just blocked it.
the entire document was automatically rejected, flagged, or deleted. The security mechanism was focused on preventing any spillage whatsoever, which created a massive, massive problem.
Utility loss.
Exactly. You had massive false positives,
Meaning what, exactly?
meaning a critical piece of actionable data, the grid coordinates of a moving enemy column, might be blocked entirely just because it contained an innocuous acronym that also happened to be used for a top-secret space program.
So you block necessary mission data.
Right. You sacrifice operational success for absolute caution.
But the sources also noted the opposite problem, which, from a security perspective, sounds much scarier. False negatives.
Indeed. Because the legacy system only checked for keywords, it couldn't understand context.
It had no nuance.
None. For instance, if a source wanted to reference a top-secret satellite program but didn't use the full formal name, maybe they just referenced the project manager's nickname, or used a slightly sanitized internal code, the binary system would miss that subtle context clue.
And the data would just flow through.
The critical classified information would flow freely to an unauthorized network, resulting in an unauthorized release or spillage, compromising the source forever.
So we have to move from that blunt hammer to something that can truly understand nuance, which is where the proposed paradigm shift comes in.
Right.
Moving to a generative AI approach powered by context-aware logic. This is where the paper policy finally meets machine learning.
This is the core innovation being proposed. The new CDS architecture completely ditches simple binary logic and keyword blacklists for complex, rigorous, machine-readable logic. And it's powered by sophisticated large language models, or LLMs.
Okay, wait a minute. When people hear LLM, they often think of, Chat GPT models trained on the entire public internet.
Right.
That sounds like a terrifying security risk if you're trying to contain top secret data. Are these models trained on the internet?
Absolutely not. And that's a crucial distinction. These LLMs are specifically deployed and trained within the secure environment.
So they're air-gapped, too.
They often are, using closed, vetted, and highly classified datasets. They are trained specifically on the nuances of military data domains. This includes millions of historical, already classified reports, sanitized disclosures, and, critically, every existing piece of the security classification guide literature.
So the training input is vetted intelligence products and classification rules, not Wikipedia.
Correct. For example, the model would be trained to understand the specific language used within domains like human intelligence or human tune, signals intelligence, SIGINT, space operations, and cyber.
So it knows the lingo.
It allows the system to check context and intent, not just isolated keywords. If the word grid appears in a SIGINT package, the LLM understands it within the semantic context of electronic collection, which is vastly different than if the same word appears in a logistics manifest.
That structural understanding of domain-specific language makes perfect sense for classification. And this structural shift leads us to the most fascinating technical part: generative reclassification, the core innovation. We're talking about the system handling that crucial downflow of data moving from, say, top secret to secret. If the legacy system could only black out words, what does the generative model do?
It performs a complete semantic rewrite.
A rewrite.
Yes. Historically, when a human redacted a document, you'd get those black bars, right? And they often made the document useless. The operational data might be preserved, but the surrounding narrative context was just gone.
You couldn't tell what was going on.
Right. The generative model, by contrast, is far more valuable because it maintains that narrative flow and operational utility while removing the sensitive information.
Okay. Give us a concrete example of how that rewriting utility works.
Let's use the example from the source material. The LLM is given a specific machine-encoded classification prompt. That prompt tells it, keep the operational utility, the coordinates, the description of the asset, but remove the sensitive source or method description. So if the original data coming across the JWICSTS network said something like, top secret satellite X detected thermal bloom and specific frequency emissions, indicating a mobile SS-26 missile launch system at grid 1A2B. This capability is attributable only to the satellite X imaging array.
Okay, so that message reveals the asset, the capability, and the location.
Yeah.
It's way too hot for our French or UK allies on a NATO secret network.
Exactly. So the generate function intervenes. It removes the sensitive source method description, the part about satellite X, the specific frequency emissions, and the U.S. attribution capability, but it preserves the operational utility.
The grid and the target description.
Right, the grid 1A to B and the description of the asset. So the output generated for the NATO secret network would be something like, high-altitude persistent sensor observes significant heat signature corresponding to a mobile short-range ballistic missile SRBM system at grid 1A2B, target validated for immediate engagement.
That is the ultimate detangling of the medium from the message. The downstream user, the Allied artillery crew, gets the precise coordinates and the target description they need to pull the trigger instantly.
Without knowing how we got the information, thus protecting the source.
And it creates a brand new, sanitized output tailored precisely to the security domain it's entering.
And it does it while adhering to all foreign disclosure rules simultaneously. And this brings up a critical, non-technical requirement.
Which is?
Authority standardization.
Okay, that makes sense. If the model is doing the rewriting, it better be working off a single authoritative rulebook. You can't have every brigade or every partner nation training its own LLM based on slightly different rules.
Absolutely not. The source emphasizes that these models cannot be homegrown by individual commands or even individual services. They must be stewarded and updated centrally by the authorized classification authorities.
The people who actually write the rules.
The ones who write the rules. This ensures absolute consistency, and critically, it builds trust across the alliance that the classification standards are being uniformly applied.
So we're basically shifting from a static, paper-based legal doctrine to executable software.
Fundamentally, yes. The Static Paper Security Classification Guide, SCG, which is the absolute Bible of classification, often a thick binder full of rules, it becomes executable code.
And that transition.
That transition, digitizing the policy itself, is perhaps the biggest bureaucratic hurdle. But it is the technological imperative that enables machine speed.
Okay, to really appreciate the scale and the speed of this context-aware CDS, we need to move beyond the abstract. We need to walk through the complex, tense scenario the sources use to validate the necessity of this machine speed architecture.
Right, the Belarus missile threat scenario.
This is a perfect illustration of the kill web in action.
It is, because it's a two-way multi-message problem. It involves mixed international partners operating on completely disparate networks.
It's the ideal proving ground. It forces us to coordinate U.S. high-side intelligence, NATO command structures, and a partner nation's ability to pull the trigger.
All of it happening across protected networks that, until now, would have required that slow, manual swivel chair.
So let's set the scene with the inputs. We have one adversary medium-range ballistic missile, or MRBM, launcher detected in Belarus. And there are three distinct simultaneous intelligence streams coming in.
and each has a different classification level.
So what's first?
First, you have the high-side inputs, our most sensitive information stream, operating on JWICS, so TSSCI. U.S. satellites detect the initial thermal bloom,
The heat signature.
that signature of the missile being prepared or launched.
Yeah.
This data is the most accurate, but it's also the most restricted. It's classified as top secret and often no foreign.
Meaning no foreign distribution.
Exactly. At the same time, you have forward deployed F-35s operating with their own top secret sensors, triangulating electronic emissions from the target.
So that gives us the location and the nature of the threat?
It does. That information is locked down tight, but it's not enough to fire on its own. It needs external confirmation, it needs validation.
And that's where the low-side input comes in. And this presents what the source calls the fascinating up-classification challenge.
It really is fascinating.
Right.
So we have a specialized human source, a human asset, operating near the target area. This person provides visual confirmation and a precise grid reference.
But they're providing this over what kind of network?
A secure but unclassified, or SBU,
Hmm.
network, something like a vetted partner app on a secure device.
So on its own, that visual confirmation is unclassified, but now it's hitting the system at the exact same moment as top secret satellite data.
Exactly. And when the CDS ingests that SBU human data, it immediately fuses it with the high-side TS satellite data. And this is where the machine-encoded logic of the context-aware CDS kicks in.
It sees both pieces of data.
The model recognizes that the combination of those seemingly disparate elements, the TS thermal bloom plus the SBU visual confirmation, validates the target with exceptionally high fidelity.
So the unclassified visual confirmation has, just by being combined with the TS data, become an integral part of a top secret firing solution package.
That is the aggregation problem solved instantly by the machine
So the CDS stops being a simple firewall that just blocks data.
and starts functioning as a sophisticated multi-port router that validates and aggregates data from multiple sources.
So what happens next? Once that data is fused and the system recognizes the high fidelity threat.
The beauty of the generative CDS is its speed and its ability to tailor the release. The system uses that machine-encoded targeting SCG model, that policies code we talked about, to instantly generate distinct sanitized outputs for specific allied networks simultaneously.
And it adheres to different disclosure rules for each one.
For each one.
Okay, let's walk through those two output paths. First up, France.
Output A is routing to France on the NATO secret network. The French fire control system operates on the NATO Secret Wide Area Network, or WAN, and they have a specific capability to engage this target.
So what does the CDS have to do?
The CDS is tasked with generating a firing solution that is specifically stripped of U.S. no foreign sourcing. It cannot reveal that the data originated from U.S. satellites or F-35s.
So the LLM does the rewrite.
The LLM performs the generative rewrite based on that SCG rule. Disclose utility, mask U.S. source. The data is also formatted precisely for the French system's software interface, and that package is then instantly queued for execution on the NATO secret WAN.
At the very same millisecond, the system has to handle the UK requirements.
Right. Output B routes to the UK Secret Ministry of Defense, or MOD, net. This output requires different sanitization. The system has to adhere to specific UK data sovereignty tags and perhaps include specific formatting required for their long-range precision fire systems.
So the model generates a completely separate output.
A separate, specifically tailored output for the UK system. So what we've just achieved here is two separate, functionally identical yet legally released and contextually distinct classified outputs,
Tailored for two separate allied systems.
originating from a core data set that was previously restricted to U.S. top-secret SCI systems only.
And the entire process, ingestion, aggregation, sanitization, and that simultaneous routing, it happens in the time it takes a human to just orient themselves in their air-gapped swivel chair.
The latency is almost zero.
And that is the operational difference between mission success and mission failure.
Absolutely. The aggregated target data instantly flows to the Combined Joint Force Land Component Command, or CJFLCC. In this scenario, that authority includes U.S. Army, Europe, and Africa, USARE-RF, and Allied Land Command, or LANDCOM.
And because the data arrived, validated, and pre-formatted,
The Human Command Authority can approve the fire mission almost immediately.
and here's the critical operational detail that closes this whole loop: the execution itself.
The machine speed CDS automatically routes the execute command upon authorization. There is no manual intervention. The French battery engages the target on the NATO secret network.
But for a successful kill web, the data flow isn't just one way.
No, the loop has to close. This requires the BDA, or battle damage assessment loop the reverse flow of confirmation.
So the French battery reports shot fired and rounds complete on the NATO's secret network. That message then flows back into the CDS. This must be the reverse translation challenge.
It is. The CDS ingests this NATO secret report. Now, it can simply push the specific raw message up to the highest level because that message often contains sensitive French unit metadata or operational procedures or specific foreign disclosure restrictions.
So it has to sanitize it again.
It performs reverse sanitization. It strips the specific French unit metadata if required by the disclosure rules, and then it pushes the notification up to the top secret domain on JWICS and across to the SBU network.
Okay, wait. Why is BDA confirmation needed on the top secret network? The target's hit, why go back up?
For immediate automated sensor retasking, the system uses that shot complete message as an instantaneous trigger to automatically cue the high side space and F-35 sensors, the TS assets, to scan the target grid for thermal residue, secondary explosions, or physical destruction. It closes the loop by leveraging the most sensitive, high-resolution assets for immediate autonomous verification of the strike effects.
And what about the original low-side Humite source? That person on the SBU network still needs to verify the outcome, but you can't tell them that NATO or France just launched artillery.
Precisely. That source receives a simplified verify effects tasking. Again, the CDS uses its generative rewrite function to create a version that is highly sanitized for the SBU network.
And the prompt for that tasking is very specific.
Very specific. It ensures that the tasking requests visual confirmation of the strike without mentioning NATO involvement, French artillery, or U.S. satellite usage. It might simply ask the source, please verify signs of activity or lack thereof at grid 1A2B. Report any visual confirmation of physical damage.
The contrast here is what really matters. The CDS managed a dynamic, bidirectional, and secure conversation across 4 distinct classification levels.
Unclassified, SBU, NATO secret, and top secret.
And it achieved destruction and verification in minutes, which is the speed required to neutralize these fleeting targets, rather than the hours of bureaucratic lag that the manual processes would demand.
And this operational success is only achievable because we stopped treating the classification system as a paper document and started treating it as an executable software model.
The policy becomes the code.
The underlying policy, the rules of classification, are no longer contained in a binder on a foreign disclosure officer's desk. They've been digitized and rendered as executable code.
Let's really analyze the functional differences the sources present in this comparative analysis table they provide, because the shift from the static, human-based process to the dynamic, machine-based one is profound.
It really is. If you look at the comparison, the legacy swivel chair model relied on a trigger mechanism that was either a slow manual human review or a primitive static dirty word list.
The blunt hammer.
Right. In the proposed model, the trigger is purely machine-encoded classification logic. The machine decides, based on perfectly applied, vetted policy code.
And the action taken changes completely. Legacy systems use simple binary logic pass-fail or simple physical redaction that black out that killed utility.
Whereas a proposed model uses generative rephrasing, that rewrite for release function. It preserves the operational value while maintaining security.
And this is where the speed advantage comes from. The gain in latency is the entire operational justification for the cost and complexity of this program.
We move from minutes to hours, the speed of human interpretation and typing down to milliseconds, the speed of a processor running a codified algorithm.
The final 2 differences really highlight the intelligence gap between the old and new systems. The old system had virtually none in terms of context. It only knew if a keyword existed.
And the new system is domain-specific. It's trained specifically on intelligence language for space, cyber, and human error. And critically, the risk profile shifts from high human error fatigue, a constantly variable factor, to consistent logic application.
The system applies the rules perfectly, instantly, every single time.
And this consistent logic is rooted in the source material's technical appendix, which details how this policy becomes code specifically. The Machine-Readable Security Classification Guide, SEG logic. This is the functional architecture where abstract policy turns into concrete rules.
Okay, let's look at the schema and model definitions. They replace those simple, static, dirty word lists with concrete, hierarchical policy logic models for specific domains.
Right, and we see models defined not just for intelligence SCG and space SCG, but also for compliance outside of strict military security,
like law enforcement SCG and health SCG,
which are critical for managing data that might involve civilian contractors, sensitive U.S. person information, or medical records in an operational theater. In the intelligence SCG model itself, we define the acceptable classification level, secret, TS, the control system, like no foreign or reltanato, and most importantly, a structured source protection rule.
And that's the logic for the rewrite.
That is the specific logic instructing the generative model how to strip the sensitive source information while preserving utility.
The Space SCG provides some excellent, unambiguous, concrete examples of this binary policy as code in action.
Yes. The policy for satellite-derived data specifically sets specific model rules that are either true or false. It allows grid coordinates to be transferred, designated as Boolean default true.
Because coordinates are fundamental for targeting.
Right. If the system fails to find a rule, it defaults to allowing grid transfer. But the policy draws a firm line immediately after that.
It does. It explicitly disallows sensor resolution, setting it to Boolean default false.
And that's because sensor specifications, such as the satellite's exact optical resolution or its specific orbital path, are typically top-secret SCI and must never be released to a lower network. This is a nuanced, high-stakes policy decision codified into a single line of machine logic that cannot be misinterpreted by a fatigued human.
I think the inclusion of the non-military compliance checks, like for law enforcement data or protected health information, PHI-HIPAA, is a fascinating detail. It shows how comprehensive the system design is.
It demonstrates that the system has to function as a universal compliance layer, not just a military security tool. Even though PHI checks might return null in a battlefield targeting scenario, the logic includes mandatory checks to prevent accidental noncompliance with U.S. civilian or legal protections.
So if there was PII in there?
If the input data stream contains sensitive law enforcement data, like U.S. person PII, the law enforcement SCG check would immediately trigger an abort transaction command. The machine acts as a highly rigorous non-STD compliance checker before it even attempts to reclassify the military data.
Now we get to the absolute heart of the technical action. The pseudocode for the procedure process kill web target. This is the automated flowchart of the kill web in practice, showing exactly where the machine replaces the swivel chair.
The procedure starts with step 1, ingest and aggregation, combining the TS, S, and SBU inputs into one verified target package object. Then it immediately moves to step 2, domain model checks, running the policy as code checks we just discussed.
And once it's verified for general compliance, we hit the central mechanism.
Step 3, classification translation.
And this translation is driven by the core revolutionary function, generate.
This is where the magic happens.
That's where the intelligence resides. The generate function is where the LLM uses the aggregated data package and the specific prompt dictated by the classification authority. The code tells it. Rewrite targeting packet. Remove U.S.-specific satellite references. Keep grid description.
And the model does it. The model then translates that sensitive package into an authorized, perfectly formatted foreign disclosure output, like output France. This output is then immediately inserted into the network queue for instantaneous routing. There is no human involved in the transfer or the rewriting.
So that one function takes highly sensitive data and converts it into usable, release-authorized data in a single secure step, all governed by centrally vetted code. But the procedure doesn't end there. We have to reinforce the BDA loop steps shown in the pseudocode, which demonstrates true autonomy.
Absolutely. The code demonstrates a conditionality that ensures the cycle closes without human supervision. It has an automated trigger. On event, receive message from Payfinder. Status shot complete.
The instant that message is confirmed.
The system executes 2 distinct automatic taskings. First, it sends a TS tasking, send tasking, network gestures, to the U.S. satellite to immediately verify the damage. Second, it sends a tasking to the SBU network for the human source. It doesn't wait for a human to interpret the BDA and write a new tasking request. It handles the entire flow automatically.
And that SBU tasking is sanitized again by using the generate function one last time.
Yes. The prompt for that SBU rewrite specifically states, do not mention French artillery or NATO involvement. Request visual confirmation of strike effects. The logic engine intelligently manages the security profile of every single complex message in that bidirectional communication chain, ensuring lethality and security simultaneously.
This transition, then, it represents a fundamental and profound shift in how the military manages information security and alliance cooperation.
It's a total paradigm shift.
It moves from viewing information primarily as a valuable thing to be hidden and guarded at all costs, to viewing it as a dynamic stream to be intelligently filtered, sanitized, and utilized at the precise point of action and reaction.
So to summarize the findings from the source material, the implementation of these context-aware, machine learning-driven cross-domain solutions is not just an IT upgrade. It achieves two overriding strategic efficiencies for the alliance that directly impact the ability to fight and survive.
And the first, the most obvious one, is lethality. The gain in speed means the alliance closes the kill chain faster than the enemy can react. You're moving from hours of manual delay to seconds or milliseconds of automated processing.
And that is the critical technological and tactical advantage in modern high-speed conflict.
Then there's a second efficiency, which is security.
By codifying the security classification guide into executable code and using generative models for precise sanitization, we protect sources and methods more consistently and thoroughly than human reviewers ever could.
You're eliminating the variability.
You eliminate the massive variability of human fatigue, inexperience, and administrative error that perpetually plagues the manual swivel chair process.
So we've covered a lot of ground here and a lot of terminology for you to take away. The data paradox, the outdated swivel chair bottleneck, the revolutionary CDS transformation, the SCG becoming code, the concept of the dynamic kill web, and of course that core technical innovation of generative reclassification.
The recommendation from the source material is pretty unequivocal. The Alliance needs to initiate a pilot program immediately. Now, they must focus on digitizing a specific SCG, like fires or targeting, and training a generative model to manage the data flow for a specific sensor-to-shooter link. This is how you validate the full kill web concept in a controlled, live environment. This is the future of coalition warfare.
It certainly feels like it. And while the source material describes a near-perfect system designed to replace human judgment with machine logic, all to enable war-fighting speed and consistency, it does raise an important question that I think we should all mull over. If classification rules become code that automatically and instantly decides what allies can see and what they can't, what happens to trust? What happens to strategic nuance and the necessary political element of human-to-human relationships when the human foreign disclosure officer is essentially removed from the loop?
The efficiency of machine speed is undeniable, but whether the automated management of secrecy can fully replace the human diplomacy required for alliance trust, that's the strategic question we may soon have to answer.
Something profound to consider as you contemplate the future of alliance warfare. That's it for this deep dive.